Thank you very much for the lovely introduction. As you said, my name is Rouven. I work for Neo4j, mostly on the Python driver. And without further ado, let's jump right into having a look at the Async Python driver. First of all, why would we even want to do that? For our GitHub repository, we had actually a feature request up for many years now, and over 100 upvotes for a project with 700 stars. I guess this is a very strong sign that users really want async support. I reckon this will mostly have come from web developers, but most certainly not only. The web development community in Python is pretty strong, and many web frameworks support async or actually build around async. So yeah. Before I go into more details, a very quick rundown of what Async Python is. We don't have time to go into much detail because I only have a 15 minutes session here. You have an event loop in Async Python that is basically, yeah, as the name suggests, a loop that runs in the background, and you schedule tasks with a loop, and the loop will give control to tasks each in a row. So this is concurrency. You have multiple tasks doing something, but it's not parallel, like with threads where they do it at the same time. With async, it is the event loop that picks one task after the other and does round robin. At least the async IO event loop does round robin. You then have async functions, so-called coroutines, which you can register with the event loop to be executed. You can also register tasks, and I think internally coroutines are actually wrapped in tasks. And whenever such a coroutine or task encounters some IO, it actively gives away the control to the event loop. We say it yields to the event loop and says, all right, event loop, pick another coroutine to execute some work for me while I wait for this IO to come back. It could be network IO, it could be disk IO. It could actually just be sleeping because it's waiting for whatever signal. So if you compare this with threading, you will notice this big difference. With threading, it is the operating system scheduler that just all of a sudden takes away the control of the thread, and you don't, as a programmer, don't have control over when this happens or which thread gets to execute instead of the one that just got suspended, which is why you need a lot of synchronization tools like mutexes and signals and what have you. With async, the story is a little different because as long as you don't yield to the event loop, no one will take away the control. So this is a bit of a simpler model of concurrency, allowing to make some assumptions and writing some easier to understand code generally. The caveat, though, is, as I said, it is not parallel. So when you have workload that is CPU bound, because you're number crunching, for example, async will not help you because you can't give off the control to the event loop. I mean, yes, you can, but you can't crunch numbers at the same time, right? Whereas with threading, you can actually do some number crunching, and another thread can do the same in parallel. However, async IO is really good for, is really good for IO-bound tasks where you wait for a prolonged time for a network round trip, for your disk, whatever. And this is also probably the reason why it is so well received with a web community, because a network server is exactly this. You get a network request, you do some IO, load some files, maybe do a call to another API, and at the end you give back a network response. So it's basically only IO. This is why this really lends itself to this kind of work. So that was my quick rundown. We didn't do it in the first place, we thought about doing it a couple of times, but we didn't come around to it because you'll see in a second, when you write async Python, it spreads worse than COVID. As soon as you start to put an async keyword somewhere in your code base, it propagates all the way up the stack, and all of your code will all of a sudden be async. And so we figured we would have to write two drivers if you want to do that, one synchronous and one asynchronous one. And that was just not feasible, to put it bluntly. But here comes the big but. Look at this fictional piece of Python code. You see a lot of async and await in there because this is what using the driver asynchronously looks like. But it could be any code that uses async Python. I'll show you a cool trick how to turn this into a synchronous program. I'll just need to whip out my cool Microsoft Paint skills. This is how you do it. It is literally this. For most parts, you just remove all the async and await keywords, and it is synchronous. It is actually most of the time this simple that there is a Python module for you, a Python package called unasync, which does this automatically. It is a pretty stupid transpiler, you gotta say it. It just tokenizes your whole Python program, removes all the async and await, and you can customize it a little bit because, as you've seen in the previous slide, I also removed the async prefix of async graph database in the 4th line. So yeah, you customize it a little bit, and then it does this. We basically now only write an asynchronous driver. We run it through unasync and get, for free, a synchronous driver. Mostly for free, that is. There is some caution to be had, to be aware of. And at the very bottom of your stack, you will have to replace things because you can't do blocking I/O in async. I mean, yes, you can, but you will grind your whole application to a halt. So instead of using normal sockets, you use async I/Os, protocols, and streams. Instead of using from time import sleep, you do async IO.sleep, because those are these kind of methods that yield to the event loop instead of just blocking the thread. So we wrote some wrappers around normal WebSockets and not WebSockets, normal sockets, sorry, around normal TCP sockets and around async IO's protocols and streams, so that they have the same feeling from the outside, except for having to await them. And this is the glue I refer to here. And with that, well, there is an async Python driver now, and it is available since 5.0, so like a couple of months. And this is how you get to use it. Instead of doing neo4j.graphdatabase driver as a factory method to get a driver, you call neo4j.async graphdatabase.driver. And you're now in this parallel driver from which the synchronous one gets auto-generated, and all of your classes will be adjusted. Most of them will have an async prefix now. Also, there's a typo. It's not ayync graph database. But that's basically it. And now add a good pinch of async and await to your code, and out comes an asynchronous application. It is actually this simple. And because it is that simple, I felt like a brave boy today. And we are going to do this live. Let's see how the live coding goes. I know live coding in presentations is always great fun. This is a very simple application for you. We have a requirements file. It has exactly one dependency, that is Neo4j, the official Neo4j Python bolt driver, that is. And the project toml is pretty empty. It just excludes the VN from MyPy. MyPy is a static Python type checker, in case you didn't know. I will use this as a little bit of a guide rail, I would say, for this presentation. Real quick rundown of what we've got here. First, we specify some constants, our connection information, basically the URI where our Neo4j instance runs, and I hope I have it running. Yes, it's running in a Docker container on my local machine, localhost. Some credentials, and with it, we are off to the races. In our main function, as I said, there is this factory method that gives you a driver, and we then inject the driver into this example. This assertion is obviously not necessary. It is just to show you at runtime a quick check that that this is actually, what it claims to be, because type hints in Python aren't enforced at runtime. We then create a session. We run a transaction function. I will not go into detail explaining transaction functions because we are running short on time. It basically calls this function and injects a managed transaction into it on which you can run some work. This query is a pretty simple one, right? You could do this in Python way more efficiently, but it's just for demonstrating how this all works. And I think this should already be enough to explain what it does. We are going to turn it now into an asynchronous program. First of all, as I said, the entry point changes. It is now an async graph async driver. And because it is that, we'll have to put an async here. If I can type, that will work. Because the context that it gives you will now close the drivers pool when you leave this with context. And this is I/O operation. It's closing sockets. It's writing some goodbye messages to sockets, some details there. But so to be able to do anything with async or await in a function, as I said, it propagates through your whole code base. This now needs to be an async function. We now need to await example, because this will also be an async function as it does I/O. Same with this, with context, it is async now. This one is also an async driver. And this is an async driver now. This is an async session. Async session, there we go. This is also an async function now, so we have to await it. It will call an async transaction function because we are doing I/O in there. It goes all the way through your stack. We have to await this. We have to await this. Finally, the result, it's usually an iterator in synchronous Python, but async iterators can't be put into lists. So let me rewrite this real quick as a list comprehension. Record for record in result. Right, so this is equivalent right now, but it will not work because this is an asynchronous iterator, so async for. Oh yeah, I forgot to prefix this with async. And finally, the entry point will be a different one. You use async io.run, which creates an event loop, and you pass in a coroutine, which will make the event loop execute until this coroutine is done. Oh yeah, by the way, I didn't show how this synchronous one works. So we'll run it, and we are happy to see 10 records and some summary data. And let's have a look at the asynchronous one. Do some mypy to type check it. It looks good. So this should hopefully also execute properly. And happy to report, we see, again, 10 records counting from 1 to 10. Beautiful. So that was for the demo. Finally, some pitfalls I want you to be aware of. As I said earlier, don't do blocking I/O or don't do anything blocking in a coroutine. There is event loop.run in executor for this if you really need to do this, which will spin up a background thread or whatever executor you configure. And then there are some constructs in the driver that are not concurrency safe, like sessions. Don't use a session in multiple threads. Likewise, in async Python, don't use them in multiple tasks or coroutines. That will yield undefined behavior, so you don't want that. And there are some methods like asyncio.shield and asyncio.wait4. This one only until Python 3.10 because they actually fixed it in 3.11. That will, in the background, create a new task for you. So you have to check carefully what you do in asyncio to not by accident create a new task. And that's really all I had. So thank you very much for your attention. And if you have questions, I guess put them in chat because we are out of time. I will answer them happily later.
Thank you, Rouven. Thanks for this great session. That was short. So yeah, definitely get the questions in the chat and hang around there for a few minutes. Thank you, everyone. And we'll be back in a few minutes for our next session.